How do you do, ladies and gentlemen, and boys and girls, and people and teachers? I'm Julius Sumner Miller, and physics is my business. And our business is more strictly heat and temperature, but I am reminded, wearing these long asbestos gauntlets, of seeing in the public square in Hamburg, Germany, a police officer directing traffic, so attired, beautiful and neat and firm and straight like an arrow, with such gauntlets, and my wife and I stood on the corner and watched him. It was like Toscanini directing the Boston Philharmonic. It was beautiful, just wonderful to watch, and he had such pleasure, meaning a car, stop here. You, so, yeah, wonderful. But anyway, see, men must be reminded of events which are enchanting, and that makes the spirit higher. I'm going to do an experiment that I have done, I suppose, on every program throughout my lifetime. It is after von Guericke. I'm going to have a big tin can. Can you imagine? I once did this with a steel tank, 6 feet, 6 feet, 6 feet. No, this was 5, I think, and this 6. Quarter-inch steel plate with a bunghole here. We put some water in. We boil the water. You know what that means, boil the water. We drive out the air and the occluded gases. There is vapor here. I stopper it up. I take the heat energy away. And if we are sharp in our hearing, we hear. The can is being wrenched a little. The water vapor is condensing. The atmosphere is doing its thing. That's about the best place to use the word, the phrase. The atmosphere is doing its thing. We can help the atmosphere by condensing the water vapor with cold water on the outside. And you know what happens? The can is crushed. Now, we're going to do this with a big can. Can I ask you, Mr. Anderson, get the other heat under there, if you will, so we can boil that water? Right, but come over here with me. Come and see here, bitte. Here it is. Here is the can. Water has been boiling. The vapor has condensed. It is steam, we call it. I am going to. Listen. Oh, I told you. Nature and Julius Sumner Miller. We will write a new opera. Now, a little cold water. I want some applause from the people out there. That's it. Magnifique. Now, if I try to get that stopper out, it will be firmly lodged because the pressure inside is less than atmospheric. But more than that, shh. Come up here, Josh. Very quiet. Listen. Do you hear the water boiling?
Yes.
The water. Oh, no hurt. No hurt. Now we will go yonder. We will go yonder. Can I? Have I got enough?
Yes.
Have I got enough
Yes.
lead? Yes. Come with me. Here we are. This tank. Water vapor. Get the flames away. The flames away. Mache schnell. We will have an explosion. Right? Listen. Beautiful. Quiet. 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 Give me my tank of water. Cold water. Cold water. This tank is pretty rigid with these fluted edges. But watch it. Watch it, Anderson. Shh. The water's boiling inside, but it has not happened. Anderson, you try it. Easy, hold it.
Going.
Is it going?
Topsoil can in.
No, I think it will not. Although we were successful, let me assure you, in an earlier adventure, we were successful. Oh, Anderson, look here. This tank did not have those fluted rims. Do you see how much rigidity has been added to the tank?
Yes.
Good.
Reinforced.
Yeah, reinforced. Let me go back. So, you are agreed that the experiment has failed? You know I do not allow that language. The experiment did not fail. Nature does what nature has to do. We did not provide the proper provisions for nature to do it. Now, consider the following. A large-scale demonstration of a paradox. Meter stick, fingers, rough, I push them toward each other. Fingers met in the middle, stick did not tip. Now I hold the stick unsymmetric. There is more load here than here, and clearly this finger will move first. And now when the fingers are equally loaded, the fingers will meet in the middle, and the stick again did not tip. Mathematics. That's all there is. Now we're going to do it large scale. We have the shafts of two motors, the shafts, one of which can rotate this way and one that way. And we are going to lay on that a heavy plank, or 2x4 or something. And if the loads are symmetric, you can see that the thing will stay there. If now I loaded it unsymmetrically, there would be more load on one than on the other, and therefore the normal force would be greater, the friction force greater, and it would move either to the right or to the left. I'm going to accomplish the same purpose, same thing, by, say, putting a load on here. If I put it there, the friction force is greater here, there will be motion in this direction. Let us go out front and see it. Am I clear with my drag line? Here we are. Here we are. That's very good. Motor, 2x4. I'm going to plug it in, and if the load is symmetric, they will stay there. Yep. There it is. They stay there. Now, I'm going to start them again, and I'm going to put the load on this one. That means the friction force is greater here, and it will go certainly that. Well, wait a minute. I got to see which way it's rotating. Yeah, it will go that way. Watch it now. Now I'm going to load it here. It'll go that way. Proof complete. Right. I need it back, Anderson, to show the other. Notice I have to get my electric energy. Watch it now. Beautiful. Now I'm going to load it symmetrically. It'll stay right where it is. Right. Now I'm going to load it asymmetrically. It'll go that way. There it is. And a large-scale demonstration of F equals mu n. The force of friction is proportional to the normal force. And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls, and people and teachers and others? I'm Julius Sumner Miller, and physics is my business. And our business concerns itself with the case of the can which did not collapse. You remember on the last program, we had a big cylindrical vessel, chamber, and we had some water in it, and we boiled the water, and then we plugged it up here, and then we poured cold water on, and it did not go, as we say. However, after we had concluded the program, we noticed a slight yielding of the wall. We hope that this is what we hope for. So we are going to do it again. We are heating the water in here, and after a bit I'll go out there and we'll try it once again, because I do not like to, what shall I say, have things fail. Now, you know my philosophy. It is important that we subscribe to the requirements of nature. While the water is cooking, let's consider another thing. You know that if we have a surface which is reflecting, and we have, say, some energy incident this way, like a ray of light, and we draw a perpendicular to that surface, there is reflection such that that angle is equal to that. This is called the angle of incidence. This is the angle of reflection. Now, light energy behaves according to this law, and we have an instrument to show you that. Consider the following. Here is a highly reflecting metal plate. Here is an incandescent lamp, which I'll just show you quickly. And here is an array of thermocouple junctions. Thermocouple junctions, called a thermopile. See it? Thermopile. A pile of thermocouples. Got that? Now, we are going to put some radiation energy from this lamp on this plate. It will suffer some reflection according to this law. This thermopile will pick up the radiation, electromagnetic, convert it to thermal energy, and here we have a 0 centimeter, which I hope shows when I have made the right angle, the correct angle, equal to the correct angle. Watch it now. We'll just have to see this and then the meter. Oh, I don't know how you'll do it, but we need to see the meter too. Watch it. I'm bringing it in. I'm bringing it in. I can't tell when the meter is reading. Is it reading? Yes, yes. Now, watch. I'm going to go away from that angle. And now it's coming back. Now it's coming back. So, a wonderful demonstration. There is a best angle.
That's good.
There is a best angle. Now, let's do it all over again, and this time, intercept the energy, not with a shiny reflecting surface, but a highly absorbing one, a black piece of paper. Let me come back to the angle, which gives us the best energy received by the meter. I can't tell, I have to see the meter. Is that it? All right, now I'm going to interpose that piece of paper. Watch the needle now. Watch the needle now. Do you see it's going back? It's going back, showing that very little energy is being reflected. Very good. That tank out there is boiling now beautifully. Let's try it, because I feel like Otto von Guericke making a demonstration.
Josh, can you switch the gas on?
Yes, but don't switch it off yet. Now switch it off. Plug it up. Mache schnell. If we lose any, more tight.
Okay, no, that's all right, bro. Good, it's on the gasket.
Whoop, watch it. Anderson is going to be drowned. Easy. Hold it, hold it, hold it. Let me hear. Oh, the water's boiling feverishly inside. The pressure is very low. But it appears again that this tank is too firmly reinforced with those ribs, those circular ribs, Anderson, and it will not go.
Little desperado.
No, we are lost. Anderson is resorting to some ice. We are in desperation and in despair.
If it does go, we'll get drowned.
Nature has thwarted us again. Yep. Let us abandon it, Anderson. It is too bad. But I had hoped to see it. And I am reminded that I tried to do this in Uppsala, Sweden, with a huge tank made of Swedish steel, and it would not go. So I said, Swedish steel is too much for us. So, a little now aside. Problem. It went. It went. Ho, ho. It went. Oh, oh, man. Oh, it went. It went. Oh, oh, mamma mia. Did it go? Oh, did it go? Oh, no. Oh, no. No. Well, ladies and gentlemen, we did that right up smart, didn't we? Beautiful. I had given it up. I had given it up. Was this caught on camera? Was it? Well, you were on it. Oh, mamma mia. I am ready to dance for joy. Huh? Faith in physics. Yep, that's it. Faith in physics. Oh, that was wonderful. Phew. Man. Oh, this is going. Oh, mother of mine. This is. Oh. Now, when I get my composure, people, we can return to the program. My great regret is, of course, that I didn't see it. Oh, I missed that. We shall have to do it again. Right. Well, anyway, consider the following. A little exercise for you to think about. I have a vessel, not a square edge like that, a vessel, in which I have put some mercury. 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 I will now put a steel ball in that mercury. Specific gravity of mercury, 13.6. Specific gravity of iron, roughly 8. Accordingly, the ball will float with about 8/13 submerged. Show you that. Mercury, I'll turn the dish up so the camera can get it, and I'm going to float the ball in the mercury. There it is, floating. Steel floating in mercury. Incredible. You know, if you were to submerge yourself in a bath of mercury for the purpose of swimming, you'd be absolutely on the top of it. Yeah, better than swimming in the Great Salt Lake. Now, what is my question, which you can think about? Supposing I pour some water on top of the mercury, you know it will reside on top of the mercury, and supposing I inundate the ball with some water resting on top of the mercury. Question, will the ball sink or will it come up some? And that is a very good question for students at all levels, and I thank you for watching. How do you do, ladies and gentlemen, and boys and girls, and mothers and fathers, and people? I'm Julia Sumner Miller, and physics is my business, and we're talking about the business of heat and temperature and the marvelous behavior of nature in these matters. By way of introduction, so I don't forget it, you remember we had some extraordinary success, quite unpredicted, in the last program, where a huge steel drum was squeezed together by the push of the air. So, given as I am to the large scale for the people, we now have a huge steel drum. How many gallons in that? 44 gallons, a huge one. And we're going to try it again and bring to mind the memory of von Guericke. But before that, let us get a look closely at this little instrument called a Crookes radiometer. Apostrophe after the S, Sir William Crookes, turn of the century, one of the great giants of Cambridge, Rutherford, Tyndall, Searle, a massive array of them, all geniuses. Rayleigh, Lord Kelvin. You know what this thing is. I'm going to cover it up and describe it. It has 4 vanes. I'm looking down on its vertical support. This face is black, this face is black, this face is black, and that face is black. The other faces are shiny. Shiny. Very light stuff like aluminum foil or gold foil. And now this thing behaves in an extraordinary way. And would you believe it? The literature is filled with commentary about this, and it is not yet quite clear. The chamber is evacuated very highly, so there isn't much stuff in there. Now, when electromagnetic energy falls upon it, whatever the wavelength, the thing turns, always with the black faces retreating. If we get a picture of this, you can see it. These are mounted conversely. This one here, the black face is running away from me. Here, the black face is running away from me. I'm going to cover this one. It's receiving energy from the lights. Now, when I remove the mantle from this, it will likely be at rest. And watch it take up some motion. Yes, it was pretty nearly at rest, and there it goes. I can speed it up by holding a match nearby. Now remember, the thermal energy contributes little. It's the electromagnetic energy that falls on the black wing and is commuted to heat energy. Goes faster. I hope. Yes, it did. Now, question. Supposing I held up close to it. Supposing I held up. Notice that one was covered better than this. Supposing I hold up some stuff that's cold. One would say, well, it's going to radiate cold and the thing will go the other way. No. This is going to take up heat energy from that, and let's see if what I predict will happen. I say it'll slow up, it'll stop, and it'll go the other way. Now it's getting a lot of energy from the lamps here in the lecture room, but it's slowing up, isn't it, Anderson? Yeah, it should be isolated because I'm blowing hot air on it. It will slow up. Now I would like to hear from those of you who give the matter some thinking, just what's going on. But first you must read the literature to acquaint yourself with all that has been said first, because there's no point in your saying again what has been said for 100 years. Pretty nearly, 70 at least. Next commentary, next matter. The case of Hero's engine. Hero's engine. Imagine it, 500 BC. 500 BC. Which leads me to say as follows. When we first put Sputnik aloft, as in October 57, the Russians did it first, then we have done it since then abundantly, as they have. I was asked one time, what do you make of it, Professor? To which I replied as follows, quoting Ecclesiastes, there is nothing new under the sun. All the rivers run into the sea, and yet the sea is not full. Nothing new there at all. Nothing. Newton established the mechanics. Kepler established the orbits. And the Chinese, we are told by historians and anthropologists and the like, had a firecracker 20,000 years ago. And all we've done, you see, is build a bigger firecracker. It is true that there is new mathematics and computers, but there is nothing new under the sun. So Hero's engine, look at it. Beautiful, absolutely enchanting. A spherical chamber with some tubes and orifices. We put a little water in. We are boiling the water. It's coming out of the holes, and the thing is slowing up. Now you see, the vapor is coming out this way, and the thing is going the other way. Now, do not make the mistake of saying, yes, that vapor is pushing on the air, which is out here. Tut, 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 tut. This would do better in empty space, because nothing would be in the way of the stuff that's coming out. Now, the physics of this is extraordinary. If we could get a very sharp look at it, we would, friction is large in this system. We would see that the orifices are drawn down very small so as to give a high efflux velocity, which brings us to our beloved Bernoulli. And, I suppose, Torricelli. Evangelista Torricelli, his mother named him prettily. So, there you are. Hero's engine. Now another incidental matter. Davy's safety lamp. You are to imagine that I am a plebeian, a pedestrian citizen at the early years of this century, and my bread is won by chipping away coal deep in the black earth. So I go below in the mine with such a thing. Oil, kerosene or such, a wick, and a screen around the flame. And I go to a deep, dark place in the earth, and with the sweat of my brow, I chop the coal away. Davy's safety lamp. Look how safety it is. There is a flame inside, you will attest. Now, I am going to show you that there is gas coming out of this burner by turning it on over here and lighting it. There it is. There is gas there. Now I'm going to shut off the gas just by pinching the tube. And then I'm going to open it again. Oh! Huh. Well, now. Oh, that rascal has given me something to think about. There it is. I wonder why that came on twice at least. Answer. There was enough heat energy in the top of this burner to give the gas its kindling temperature. Now I'm going to, there's gas there. Oh, yes. I once did this in class. Oh, you'll be enchanted by this. I once did this in class, and to a man, the students voted, stay with it, Professor, stay with it. Isn't that, you see. Now I'm going to pour some gas around that wire screen. And an amazing thing, outside here, the gas will not flame, fire, ignite, combust, but it will inside, that which penetrates the screen. Watch it sharply. Hear it? See it burning inside? Well, it gets a little too hot and the thing smokes, so I'll wait a bit. Now watch. There it goes. The gas went inside, but the flame does not come through. There it is. I'll do it again. There it is. Oh, there's gas there. There it is. And I say that is remarkable. And now when I speak of Sir Humphrey Davy, about whom must I speak? His little bottle washer, Michael Faraday, whom he engaged to wash bottles and who spent 50 years in the Royal Institution with his wife Sarah. And I shall return another day.